Hello. Uh, so class was unfortunately canceled this evening due to the Fair St. Louis stuff that's happening around campus. So this video is going to go over the topic that I wanted to discuss in class today. Before I start, just a couple of reminders. First, your project proposal was due to me today. So if you have not sent me a project proposal yet, which there are only I think one or two people who haven't sent me a project proposal yet, you need as possible. Second, please remember that you have a homework assignment due on Tuesday, next Tuesday. And next Tuesday's class will be particularly important because we will discuss our next programming paradigm and also introduce the next homework assignment on Tuesday. So please, 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 please come to class next Tuesday. Very important class that you are not going to want to miss it. Okay, let's talk about power consumption. Just to give us a little bit of a background as to this particular discussion, the first thing that's important to know is that, for most of the history of high-performance computing, the chips that were being used were specially designed for high-performance computing. This is especially true through the 70s and the 80s and even into the 90s. And these chips were specifically designed for performance, even specific applications, some of them. So they were not necessarily as general purpose as you might consider our chips that we use today. But somewhere in the mid-90s or so, all of that changed. So personal computing came along, and that really had a large effect on the high-performance computing community as well. Again, it was late 80s, early 90s when everybody started to have their own computers. And so the chips that were being developed for these consumer-grade machines really exploded in quality and quantity, of course, as well. So high-performance computing, of course, took note of this. And these days, most high-performance computing systems rely on these commodity, these consumer-grade chips. So the chips that are being used in these computers, while they are on the high end of the scale, are the same chips that you or I could go out and buy at the store today. What makes them useful in high-performance computing then is we just need a whole lot of them, right? So I only have one chip in my laptop, as do you probably, but these high-performance computers are going to have perhaps even millions of these different chips within a single system. So they're really kind of drifting away from the specially designed, special purpose chips into more of a brute force approach where I'm going to take as much as I possibly can and throw it at a particular problem. The reason that this works, you might think, well, that's kind of a sacrifice, right? These general purpose chips aren't going to be quite as good as those specially designed chips that were used in the past. And that's true, but you have to realize that the gain here comes from that design process. Designing those special chips was not free, was not cheap. It was actually very expensive and very time consuming. These days, if you want to build a supercomputer, there is no design time at all spent on the actual chip. Now you still have to design lots of other things as well, right? The network and the topology and of course, memory, all of that fun stuff that we're going to talk about later on. But you do not have to spend time designing a chip anymore. You can just go buy a whole bunch of chips off the shelf. And so then now any changes that affect personal computing also directly affect high performance computing, which is very, very important, right? So all of that is useful to keep in your mind as we go through our discussion today on power consumption. If we think about the trajectory of personal computing within the last 10 to 20 years, through the mid-90s, early 2000s, the focus of these chips, the focus of the chips for personal computers was all about clock speed. Every time a new chip came out, you would hear all this marketing information, all of this advertising geared towards how fast it was, the clock speed, right? But then there came a point when we couldn't increase the clock speed of these chips anymore. It was just physically not possible because increasing the clock speed was generating too much heat, too much power, that we were melting the chips. So around early 2000s, early to mid 2000s, there was a shift from high clock speeds into multi-core architectures. So nowadays, right, to keep improving performance of these chips, we have to have more and more cores. The clock speed has actually remained relatively constant within the last 10 years or so. And so multi-core, of course, is what's dominating right now, but there was yet another shift in focus towards the late 2000s, especially within the last 5 years or so, which is mobile. Of course, everything personal computers now is heading towards being mobile. Desktop PCs are really being kind of phased out. You only really see them in large enterprise uses, or for the people who like to have, you know, high-end gaming PCs. But most people would prefer to have a laptop, and almost everybody now has a smartphone, has a chip in their pocket that they carry around, or a tablet, or both, right? So those shifts in personal computing have direct effects on high performance computing, especially as it relates to power consumption. Some other important factors that relate to power consumption too include the green movement. So of course, in the last 10 to 15 years, the environment has become a very important topic of conversation, not just within computing, but in general. And so that effect has also spilled into high performance computing. It's also a huge topic of conversation, something that's very much under consideration when people are building new supercomputers. So let's talk about power consumption a little bit. We'll start you off with some statistics to kind of give us a baseline here. The average house, the average US household uses roughly 1 to 2 kilowatts of power per day. So if you were to take a computer, let's say it's a very high-end computer, and you set it to do something for an entire day, an entire 24 hours, something that was very computationally intensive, right? So that it was actually active. That computer, that high-end machine, would use about 3 to 4 kilowatts of power within a single day. So consider that's just one chip, right? These computers, as a proportion of our total household footprint, are a very large portion of the power that's being consumed by people today. And so if we extend this example out, right, to high performance computing, those numbers add up very, very quickly. The Tianhe supercomputer, the fastest supercomputer in the world, #1 on the top 500, just to run the LINPACK test, just to run the LINPACK benchmark test, it used more power than an entire average US household would use in a single year, just to run that test. And so if you want to put dollar figures on this, right, let's say that we price it out at even 10 cents per kilowatt, right? This thing is using 17,000 kilowatts of power to run that LINPACK test. So we're talking about $1,700 just to run that test, just for power, just for the electricity that the machine requires to run that particular benchmark. That is a staggering figure. $2,000 just to keep that thing on for the duration of the test. So these things add up, not just from a power consumption point of view, but also from a cost point of view. So what are some techniques then in order to help us reduce power consumption, to make these machines more efficient? Well, there are several techniques in common use. And again, remember that these techniques are in use on personal machines as well, because the chips that are being used in these high-performance machines, in these supercomputers, are the same chips that you have in your laptop, right? The same chips that you have in your personal computer. So we just have to look at what personal computing is doing to limit power consumption and apply that to high-performance computing. So over the top of the list, you see frequency scaling. right? So this is the act of changing the clock speed based on how busy the chip is. If you see that there's not a whole lot going on, right, the chip is lightly loaded, then we can scale the clock frequency down, and this provides the effect of not drawing as much power through the transistors since they aren't switching as often. So frequency scaling is very, very common. Almost all chips that are shipped these days are using some form of frequency scaling. Parallel scaling is actually this idea of multi-core chips, right? So I am including more chips, or I'm sorry, more cores on a single chip. But one of those cores is generating actually less power, right, than the single core architectures that we had in the past. So, you know, while the chip on a whole might be drawing more power, the individual cores themselves are drawing less power. So it's less power per core, is this idea of parallel scaling for power consumption. GPUs are a very, very popular way of reducing power consumption, especially within high performance computing. In general, GPUs require a lot of power to run. If you've ever built a gaming PC, you probably are aware of this. They require a heavy duty power supply. So in terms of absolute power, GPUs, you know, not the greatest thing. However, one important thing to keep in mind is the efficiency. So how much processing power are we getting for the power that's being consumed? And that's where GPUs really shine. They require more power, but they're also extremely, extremely efficient at how they use that power. So GPUs are a great tool for providing power efficiency. And then a couple remaining techniques that we see down here are power gating, which actually uses this concept of a sleep transistor. And what that sleep transistor does is if it sees a stage of the pipeline or some piece of the chip that's not being used, that sleep transistor will activate and actually turn the entire section of the chip off so that it is no longer drawing any power. And then clock gating is a similar idea where instead of turning the chip off physically, you know, shutting off the transistors, we simply will restrict where the clock is going within the chip. So maybe the transistors are still on, but since the clock is not being fed into a particular part of the chip that's not in use, the transistors aren't switching. So we're not going to lose the power that it takes to switch a transistor. So, you know, it's interesting to note that in terms of the actual power that's being used per transistor, that value is going down. Transistors themselves are becoming more efficient, which is a good thing. The bad thing, the downside of that is, you know, overall consumption is still up. So how does that happen? What does that mean, right? Well, the average power per transistor is down, but we're packing more and more and more transistors onto these chips, right? So, you know, it's nice that we're making more efficient transistors, but it's allowing us to use more of them, so the overall power consumption is going up. In addition to that, as transistors get smaller and smaller and smaller, the leakages from these transistors get worse and worse, and that's actually where a lot of the additional power consumption is coming from these days. Is all of those transistors, every transistor leaks power, and so the more transistors you have, the more leakage you're going to accrue in your CPU. So those traditional multi-core CPUs, right? Mobile CPUs was another topic that I brought up at the beginning of this presentation, right? So is there any market for mobile computing with that in high performance computing? And the answer is yes. A few years back, there was a group in Spain that was constructing a high performance computer using ARM chips, the same chips that you have in your phone. And actually, while I was not able to find any progress on that computer, which implies that it's still being designed and built, what I did find was that Lenovo, a very popular computing manufacturer, has also started designing a prototype using mobile CPUs. for supercomputing, and they're planning to develop this for sale, for consumer grade sale, to business, to enterprise level computing needs. So they're basically hoping to create something that is high performing with these ARM chips, which are very low power by design, right? That's the benefit of these mobile CPUs, is that they're designed to be low power, because for a phone, the most important thing to most people is battery life. How long can this thing stay on? So these mobile CPUs, which are very power efficient, are an interesting prospect for high performance computing, but as of right now, still sort of a developing field. It'll be an interesting thing to keep an eye on that over the next few years, and see how mobile computing helps high performance computing evolve. Let's talk about some other power consumption techniques. In fact, you can't really talk about power consumption without also talking about its cousin, which is heat dissipation, right? So if I'm ever running a lot of power through something, it's going to generate a significant amount of heat. And so power consumption and heat dissipation really go hand in hand. You can't have one without the other. And so heat dissipation also has a huge effect on the efficiency of a particular system. So this is worth talking about as well. Just to give you an example of how important it is, the Tianhe supercomputer, the #1 supercomputer in the world, requires 6 megawatts of power just to keep the system cool, right? So they're drawing lots of power just to keep this machine cool enough to keep running. And there's a very direct relationship between the two, right? The hotter my chips get, the less efficient they're going to be, the more power they're going to leak. So really it is in the best interest not just to keep your chips from melting, right? Which of course is the primary goal of heat dissipation. We don't want our things to melt. We don't want to damage our computers. But also from an efficiency standpoint, our computer will be better performing if we can get this heat out of there. So how's it done? I'm sure that a lot of you are already aware of some of the more common techniques that are used for heat dissipation. So things like air cooling, which is fans, right? Almost every computer ships with a fan. Some of you may even have some experience with liquid cooling, so water, using water to build pipes that run through the system. The water absorbs the heat, and then we pump the water out of the system, and the water takes the heat with it, right, is the general idea behind liquid cooling. And then heat sinks are also relatively common, typically glued directly to the chip to help dissipate heat. The idea behind a heat sink is that the chip has a relatively small surface area, but a heat sink expands that surface area significantly so that we can get more heat out of the chip faster than we could with the chip's original small surface area. So those are fairly common techniques for heat dissipation. What I would like to talk to you about actually though are some of the more uncommon techniques for heat dissipation. So we won't talk about all of these in detail, but we will talk about a few of these. So liquid submersion is a very interesting one, actually taking a computer and submersing it in a liquid of some sort. I do have some examples of that I want to talk to you about in just a few minutes. Phase change is another interesting one where we actually use the heat to change the phase of matter, either from frozen to liquid or liquid to gas, right? With the idea being that the amount of energy required to change the phase of something is higher than if you're just heating up liquid, for example. And then you can also use some exotic liquids like nitrogen or helium or freon, basically the same kind of stuff you might expect. In freon is what you have in your air conditioners, right? Liquid nitrogen, is one of the coldest materials on the planet. So those can also be used to potentially cool your computer down, although very much on the extreme end of things. And then we also have thermoelectric. So thermoelectric heat dissipation is interesting. It requires a junction of two materials. On one side, we have material that's going to be very heat absorbent, that's going to basically take on all of the heat from the system. And then the flux between that material and the material on the alternate side, right, helps dissipate that heat very, very quickly. That was kind of a high-level, watered-down explanation of how it works. But the pros of this approach are there's no moving parts. It's basically two pieces of material that are fastened together somehow, right? So that is a nice thing. It can't really break. It's just a static piece of material. Very scalable. If I want to make it, if I want to dissipate more heat, I just add some more material. I just make it bigger, right? The disadvantage of this is it's not particularly effective. It's not particularly efficient at dissipating heat. So, I bring this up because it is very interesting. I find it fascinating. I'm a big fan of physics, and this is directly related to physics, thermodynamics, right? The only place that it's find a lot of common usage is in satellites, where one face of the satellite is commonly pointed directly at the sun, which, as I'm sure you know, generates quite a large amount of heat, right? And then the side that is not facing the sun will be this special heat dissipating material that can be used. So let's talk about something that's perhaps a little bit more practical for our purposes in high performance computing. Liquid submersion. So this idea of liquid submersion is very, very interesting. We take a computer and we actually dip it into a liquid. We submerge these components into something that is thermally conductive. What that means is that it conducts heat. So the liquid is going to take the heat that's being produced by the system. However, this same liquid, of course, cannot be electrically conductive. So it has to be something that's inert electrically. Otherwise, we would short the system. Nothing would work, right? So water is out. That would be a horrible liquid to use. What kinds of liquids do work? Typically dielectrics. So, we say dielectrics. What do we mean by that? Used oftentimes in capacitors, but, if you want, there's very specialized versions of dielectrics that you can go out and buy. But if you want to think of some common examples of dielectrics, cooking oil or motor oil or silicone oil would be examples of things that are good at conducting heat but will not conduct electricity. In fact, if you go on YouTube and do a search for computers submerged in cooking oil, you'll find videos of people doing just that. It's pretty interesting. People are actually doing this. It's not very commonplace, but it is starting to pick up some traction. Transformers, power transformers do this actually. So transformers, of course, generate lots of heat. And this is a very efficient way of cooling them off. In terms of supercomputers, there are some examples as well. The Cray 2 computer from 1985 did this. It was very, very novel, very, very unique at the time, right? It had a whopping 1.9 gigaflops. This was before the top 500 existed, so we can't tell how fast that was in relation to other computers of the era. But it was a bona fide supercomputer that did submerge itself in this specialized dielectric used by Cray. The downside of this, of course, was if they ever needed to provide maintenance on this machine, they had to drain all of the liquid out and then perform the maintenance and then refill all of that liquid again, which is a very time-consuming, tedious process. In fact, that ended up being the downside. The demise of that particular system was that the power failures occurred too frequently for it to actually be a practical computer. But there is yet another more modern example of this taking place. A very interesting computer called the Tsubame KFC. So this computer was just created within the last 2 to 3 years. Oh, and actually this slide is out of date. It's got over 2,900 CPU cores now. And all of them, every single one, is submerged into mineral oil. So this entire computer is submerged in oil. And this computer is capable of generating 4.5 gigaflops per watt. So it's very, very efficient. Very, very efficient. I don't know the actual I don't know the actual gigaflops rating for it. I think I actually have it on a future slide here. So it's not the fastest computer in the world, or not even in the top 10, actually. Later on, we'll see exactly where it falls on the top 500. But it is very, very extremely power efficient. So this idea of submerging a computer into liquid is a very efficient way of doing things. This computer is in Japan, so you can probably tell by the name that it is coming from Japan. And the fact that it's in Japan is a pretty interesting thing to discuss. The reason that this computer exists is because of the Fukushima power plant disaster that occurred, I believe, in 2010. So 4 to 5 years ago when that disaster occurred. It was a very big deal at the time, a very costly disaster for the country of Japan. And it really made them focus, really made them think about their energy consumption, because when this power plant went down, right, there were a lot of repercussions, not just in terms of the disaster, but also in terms of power consumption within the country of Japan. And so the country has sort of entered this huge green kick, and this supercomputer is an extension of that. A very, very, very efficient supercomputer. This thing is pretty cool. Here's a picture of it that I found online. You can see down here, I don't know if you can see my mouse pointer or not, but on the right side of the screen, those are racks. Those are server racks. And then on the left side of the screen, you see all those tubes. Those are the tubes that are cycling the liquid into these machines. And then it's kind of hard to see, but all of these are in fact submerged under liquid, under mineral oil. So this entire supercomputer, all of these banks of server racks are submerged inside of this mineral oil. And you can see that there are even lights on. This computer is running. This computer is executing a program as it is submerged in liquid. So it's a pretty fascinating machine. One of my favorite examples of innovation within the field of high-performance computing. Okay, so another interesting idea within the world of heat dissipation that's been gaining traction within the last few years is this concept of hot water cooling. So the idea behind this hot water cooling method of heat dissipation is that the temperature of the components, the temperature of these chips is much, much higher than room temperature. They get really, really hot. And so we don't necessarily need to use cold water here. We don't necessarily need to use chilled water to cool these chips down. Even if we ran room temperature water through there, right, since room temperature is still colder than the chips, then that room temperature water would still wick some of that heat away. It would still help dissipate some of that extraneous heat within the system. It wouldn't be as efficient, right? That hot water, that warmer water is not going to be able to accept as much heat as cold water would, but it would still take some away. And so this would save energy, right? Because most water cooling systems have to cool the water first, which requires energy. To make water cold, we have to use energy to cool it down. In practice, this has been done with room temperature water. This has also been done with water up to 113 degrees Fahrenheit. So that's actually fairly warm, right? That's pretty warm water being used here. And there are some other advantages of this as well. We can actually use this to replace hot water heaters within certain buildings. In fact, if you look online, you'll see several examples of this where they use the hot water coming out from their water cooling systems to provide hot water for the buildings that the computers reside in. Some other clever techniques that have been used in terms of water cooling include I believe it's a Facebook data center up in Norway that's built on top of a natural spring. So they use this naturally cold spring water so they don't have to chill the water first, right, to pipe it through their systems. And it's very, very energy efficient. One of the most energy efficient data centers in the world, but it's in the middle of Norway, like out in the middle of nowhere. So yeah, that's maybe the one downside of that particular data center. In terms of hot water cooling, some practical examples of who's doing this. Sequoia, which is the #3 supercomputer in the world on the top 500. I believe that's the one that's at Lawrence Livermore National Laboratory, does this. They use hot water cooling. Also, the IBM SuperMUC computer, which is #14 on the top 500, also does this. eBay does this with their data centers, right? So hot water cooling is catching on, and I expect to see actually more of it throughout the next several years. Another interesting idea that's been proposed recently in terms of water cooling, I recently read a paper that suggested piping water directly through the chip. And so there is a company, I forget who it was, I believe it might be IBM, but I'm not, or Intel. I can't exactly remember, but there's a company who's designing chips with little pipes that run directly through the chips themselves, which I find fascinating. You know, traditional water cooling as it exists today, brings the water as close to the chip as possible. Basically, the tubes are touching the chip. They're on the surface of the chip, right? Sitting almost directly next to the chip. But this new idea would actually pump water through the computer chip using very, very, very small tubes. With the idea being that since it's even closer to the source of the heat, it would be more efficient at dissipating that particular heat from the chip. Of course, the disadvantages being, you know, if something happens to that tube, if the water leaks, right, then the chip is done. The chip is going to be fried, which is why I'm sure they're taking their time and trying to do this right, so that they don't break things along the way. But very, very interesting idea. So for the vast majority of high performance computing, what do they use? Well, the somewhat disappointing answer, somewhat anticlimactic answer is that they use the same thing that we use. They use fans, they use water, and they use heat sinks. The only difference between what they're doing with their computers and what we're doing with our computers is that it's on a much, much, much larger scale. They have a lot more chips to cool than we do, right, in our laptops. In fact, I recently read an article about Titan, which is in Austin, Texas, I believe. Their fans are so big and so loud that you are required to wear earplugs if you are walking through the server room that contains Titan while it's executing. So, you know, they're using the same process as everybody else. They're just doing it on a much larger scale. Why is this? We talked about, you know, how efficient liquid submersion is. We talked about the interesting idea of hot water cooling. Why aren't more people using those, you know, interesting ideas, those novel ideas? And the answer, unsurprisingly, is cost. Fans are cheap. You know, heat sinks are very cheap, very, very, very cheap. Water cooling is even relatively inexpensive. So it all boils down to how much these systems cost. You have to consider that they've already devoted, you know, millions of dollars to create this system. Using a fancy heat dissipation system is only going to increase the expense of designing and building one of these computers. So they keep it basic. They keep it as simple as it possibly can be. Okay, so that's sort of a basic overview of, you know, power consumption and heat dissipation that I wanted to talk to you about. Now let's talk about, you know, how can we measure our effectiveness? How can we measure how efficient something is? It's easy to reduce power consumption in a computer. All you have to do is turn it off. If I turn my computer off, it consumes no power whatsoever. But that's sort of a, you know, not an ideal answer to the question of reducing power consumption. We want to reduce power consumption while the computer is running, so we can't ignore the factor of performance. So it's really two things that we care about. We do care about performance, right? Performance is key. We want our computers to be very high performing. We also want them to be power efficient. And so what's usually used to talk about power efficiency in the world of high performance computing is flops per watt. flops being that floating point operations per second metric that we talked about a couple weeks back. That is the metric that is used within the top 500, right? And then watts being how much power is actually consumed during a particular operation. And so the most important metric for power consumption within high performance computing is flops per watt. We want to get the most flops as possible for each watt that we consume. Another metric that is sometimes used is this swap metric, which is a factor of performance, whether that means flops or something else, over the amount of space that it takes up. Right? How big is this times the power? So it also takes space considerations into account. This is important, especially for data centers, for very large data centers. You'll see this swap number used to reference the efficiency of a particular data center. But for our purposes, I want to talk to you about this flops per watt metric. There is a list that actually tracks flops per watt for various high-performing computers, and surprisingly, it's called, the green 500. So it's based off of top 500. The difference is, instead of just caring about flops, they care about flops per watt. And so the flops part is achieved using LINPACK, using HP LINPACK, right? In fact, the flops metric is the same flops metric that is submitted to top 500. It is only the actual flops metric that was achieved. It's not the theoretical maximum flops metric. So it's only actual physically measured performance that is taken into consideration for the green 500. And then for the watts measurement, it's the average power consumption over this LINPACK run, which kind of brings up an interesting question: is how do they actually know this? How do they determine average power consumption for these massive machines? If you or I want to know how much power something costs, right, we have to go out and buy a meter. We can plug it into the wall and then plug stuff into the meter and see how much power it consumes. But for a high performance computer, that's really not realistic, because each server is going to be consuming power individually, and it all depends on how well that load is balanced, right? So you kind of have to take these power figures with a little bit of a grain of salt. The way that they actually compute them is by monitoring the power consumption for a rack, or maybe a few racks, a very small subset of the overall system, and then using that to project an overall estimate for the entire system, because it's simply impractical to actually measure the entire power consumption for the entire system. Not impossible, just impractical to do so. So just keep that in mind as we go through and we talk about the following statistics. So who do you expect to be on top of the green 500, right? Who's going to be number one? Well, it's actually currently, this is the most recent list from November of last year. They haven't released the list for July of this year yet, although they will soon. Now, we'll be sure to talk about that when it happens. But you see this GSI Helmholtz Center computer is the number one computer in the world in terms of power efficiency, with 5.2 gigaflops per watt, right? So very, very, very efficient. You can see that number two is about 300 less than that, and it drops off pretty quickly as you go down the top 10 in terms of power efficiency. And so you can see over on the right-hand column the total power that was used to perform the LINPACK benchmark. What they don't show you is the actual flops rating for each of these computers. I think it's interesting to compare this list with the top 500. This computer, the number one computer on the green 500, comes in at 168 on the most recent top 500 list. So, not a bad result, not a bad computer in terms of performance, right? But also not top tier either. So the most, and that's a pretty common theme. The most efficient computers are typically not the fastest computers. Although there are some interesting exceptions to that rule. If you scroll down to, let's see, looks like it's down number 3 right here. here's our that computer that we were talking about earlier, the Tsubame KFC, right? So this is that liquid submerged computer that we talked about being highly, highly efficient. So it is the third most efficient supercomputer in the entire world. But in terms of top 500, right, this ranks 392nd on the top 500 list. So even worse in terms of performance, in terms of overall performance, than the #1 most efficient computer in the world. We can go the other direction too. If you look at the Tianhe, the fastest supercomputer in the world right now, in terms of the green 500, it comes on the list at number 57. So very, very fast, moderately performance, moderately efficient in terms of power consumption, right? And so you can take a look at all of these values on the Green 500 website, which I've actually linked to on the course calendar page, right? Perhaps the best computer, the fastest computer on here in terms of performance, I believe is this PIZ-DAINT one down here at number 9. I don't actually have it written down in my notes where it falls on the top 500, but it is a very fast computer used for climate modeling. Another thing to notice actually about these computers that you see on here, almost all of them are using some sort of GPU. So if you look at the top one, actually here, so starting with number 3 and working your way down, you see NVIDIA K20X for number 3, NVIDIA, right? So that all indicates that they're using GPUs to augment these. Oh, the first one has AMD, not NVIDIA GPUs. In fact, the only one that doesn't look like it has any sort of GPU included is number in this list, the Soren computer. So, you know, it's a combination of things that makes something efficient. For example, this Tsubame computer relies not just on the unique liquid submersion concept, but also relies on using GPUs, which are very, very efficient when it comes to power consumption in order to generate such a high rating. And so it's also interesting to take a look at how these ratings change over time, right? And you can see on this particular plot, the Green 500 only goes back to, I think, 2008 or 2007. And you can see the megaflops per watt. Notice this is a log scale here on the y-axis, to put this in a little bit of context. But you can see that for the best computers, this value is going up. So the efficiency is going up. But what's more important, I think, is actually the blue line on the bottom there that shows that even across, you know, the entire top 500 power efficiency is going up. So it's not just the best computers. It's not just a, you know, a subset of computers that's focused on power efficiency. It is all of the high performance computing. In fact, it might be hard to see from this slide, but the slope of the number 500 line is going up a little bit faster than the slope of the number 1 of the top most efficient computer in the world. And ideally, we would like to see, you know, all computers being as efficient as possible, so that this gap gets even closer and closer than it is now. So power consumption is really, really taking, has the attention of the high performance computing community, and it's become a major topic worth addressing. So to kind of wrap things up here, to bring this topic to a close, of course, it's very important. Consumption of power is up, and actually I don't see that slowing down anytime soon. The total amount of power consumed is going to keep going up, but hopefully efficiency of that power consumption will also go up at the same time. That is the ultimate goal, right? We're going to need to use more power to get more performance. That's just a fact. But we want to make efficient use of the power that we're consuming. So further changes in personal computing will drive these power consumption goals. I'm very, very interested to see how mobile computing affects high performance computing, not just within the realm of power consumption, but just in general, right? And I'm also interested to see what kinds of cooling systems start to take hold over the next few years. Will we see more liquid submerged computers? Will we see more hot water cooling? I hope so. I really do. They come with challenges, but those challenges do have a significant payoff. So that wraps up my discussion for today. It was pretty quick. Normally I'd open up the floor for questions, but of course, since class is canceled tonight, I unfortunately cannot do that. But if you do have any questions about this topic, I would encourage you to either email me or ask on Piazza, or take a look at the resources that I've linked to on the course website about the Green 500 and about the Tsugami KFC. This would be a great topic to expand upon, actually, for one of your projects, if this is something that's caught your interest. So just keep that in mind. This would be a great topic for one of those things, should you choose to do so. So that about wraps it up for me today. Thanks a lot, and I will see you guys on Tuesday. Enjoy your 4th of July weekend.